Good day and welcome back for our third and final installment of an introduction to functions of several variables. In this video, we have two examples, and we are at the opportune time for you to work through and practice some of these concepts. What I would like you to do is to pause the video and spend, I don't know, upwards of maybe 5-6 minutes and see if you can answer the questions that are asked. Now that you've spent a few minutes working on these examples, and if you haven't, pause the video and spend a few minutes. So for the first problem, we're asked to sketch the graph of some function of two variables. And remember, this is a fancy way of asking us to sketch all points of the form x, y, z, where z is the associated output. So z is equal to 10 minus 2x minus 5y. And at this point, in order to sketch the graph of a function of two variables, we have to recognize what surface is being described by the relationship we have between the x, the y, and the z. And this is a common example that we've encountered earlier in the course. Note that if you move the x and the y terms to the left and you have 2x plus 5y plus z equals 10, this is a common equation. This is a plane. And in order to sketch the plane, or at least the portion of it in the first octant, we can really think of three key points to consider. What we can consider would be the intercepts of the positive x, y, and z axes. So for the x-intercept, we would have a point of the form something 0, 0. The y-intercept, 0, something 0. And the z-intercept, 0, 0, something. And purely by inspection, we can note if y and z are both 0, x must be 5. Similarly, if x and z are both 0, 5y would be 10, so y is equal to 2. And if x and y are 0, z must be equal to 10. And the picture we're going to draw might not be exactly to scale, but that's why we label key intercepts. So we have our z-intercept as 0, 0, 10, our x-intercept as 5, 0, 0, and our y-intercept as 0, 2, 0. And we need the portion of the plane sitting in the first octant that passes through those 3 points. And that would be the triangle formed by those points. So in red, we have the desired surface. For the second example, we're asked something slightly different than we've been asked in previous examples. We're given a contour map, and we're thinking of this contour map as representing the temperature at a specific location. So for example, if I'm on this 70 contour, that would indicate that any point on that contour, the temperature would be 70 degrees. If you're on the 80 contour, any point on that contour, the temperature would be 80 degrees, and so on. And then you have to keep in mind that in between the contours, so as you move from the 70 to the 80 contour, the temperature at that location is going to slowly increase to 80 degrees. The closer you are to the 80 contour, the closer your temperature will be to 80 degrees. So let's go ahead and estimate a few things based upon this contour map. The first thing we're going to do is estimate the temperature at alpha Berg. And we'll call that T sub alpha. So note the location of alpha Berg on the contour map. It's in between the 80 and the 90 contour. So we can say that the temperature is between 80 and 90 degrees. It won't be 90 degrees, it won't be 80 degrees because it's in between the contours, but we note that it's closer to the 90 contour than it is to the 80 contour. So a reasonable guess would maybe be, in this case, I'm going to say 88 degrees. But if you were looking at this and you wanted to say 89 degrees, 87 degrees, those are reasonable estimates to make. Okay, so similarly here, estimate the temperature at gamma estates. So if we let that be T sub gamma, we see that gamma estates is also between the 80 and the 90 degree contour. So we can once again make the observation that 80 is less than T sub gamma is less than 90. But in this case, when we make our guess for the value or the temperature at gamma estates, it's closer to the 80 contour than it is to the 90. So in this case, I'm going to go ahead and say maybe 84 degrees, just to give it an estimate. And once again, if you were to say 83 degrees, 85 degrees, those are all reasonable estimates to make. Now, in terms of the hottest temperature, so let's call this T sub H for where it is the hottest. If we look at our contours, we see that they're spread out every 10 degrees. And we have 60, 70, 80, 90, 100. If the temperature was 110 degrees somewhere, there would be a 110 contour. So at this point, the observation that we can make is that 100 is less than the hottest temperature, and the hottest temperature is also less than 110. And we can see exactly where this is going to occur when we're in the inside contour. The temperature is greater than 100 degrees. But we also know it's less than 110. So leaving it at this point is really the best we can do, which completes the material for this current video. So in the next section, we will begin working our way towards differentiation of functions of multiple variables, which means we first have to start talking about things like limits and continuity. So stay tuned and take care.